All right, guys, let's take a look at today's lesson. We have actually 3 things to work through. We're going to learn algebraic substitution, which is basically in addition to the substitution techniques that we've been learning. We also are going to talk about even and odd and how we can work integrals with that information. And then lastly, we're going to talk about some Riemann sum stuff. So let's start out with our algebraic substitution. Sometimes when we'll work through a substitution and we have an extra x left over, sometimes we can account for that using this technique called algebraic substitution. Not always. We can't always handle it this way, but many times we can. So let's look at our very first one. We would set u equal to 2x minus 1, so du would be 2 dx. So we move the 1/2 over. And we see that we have an additional x left over. And so this is how sometimes we can handle that by using algebraic substitution. What we do is we go back to the original u substitution that we created and we solve for x. So I would move the 1 over, so it would be u plus 1 and divide by 2. So x is going to be 1/2 times u plus 1. And so what we'll do is we're going to go ahead and sub everything in. And if it's possible to simplify once we've done that, then this technique will work. So let's see. For x, I'm going to go ahead and pull out that 1/2 here. For x, we would have u plus 1. And then we have square root of 2x minus 1, which was our u. So u to the 1/2 du. We have all the x's taken care of, and we also can simplify that into a form that we can work with. Yeah, we have another 1/2. Okay, I took my original substitution and I solved for x. Move the 1 over, divided by 2, that gave me my expression for x. Okay, I took my 1/2, actually I had 2 different 1/2s to move out. And we're going to turn that into 1/4 in just a moment. And then I replace the x with the u plus 1. There's my times 1/2. And then I replace this with u. So if what we get now we can work with, then this technique will be successful. There will be times when we can't. But we can. We can actually distribute that u to the 1/2. And so we'll rewrite. Let's see, u times u to the 1/2 is u to the 3/2, and then u times 1 is u to the 1/2. Okay, hopefully we are not tempted to try to do some kind of a chain rule or product rule, because there is no chain rule and product rule in integration. We have to actually, in this case, be able to multiply it out, which we can. It is u to the 3/2. I'm not sure what your question is. Okay. So the du is telling us what to integrate, and the absolute proper way to do it would be to put this entire first thing in parentheses, which you can if you want to. We've been leaving the parentheses off, but that would be the proper way to do it. Okay. Any other questions? Okay. So now we simply do our reversal power rule. We have 1/4 times, so 3/2 plus 1 is 5/2. So 2/5 u to the 5/2. And 1/2 plus 1 is 3/2, so 2/3 u to the 3/2 plus c. I'm going to go ahead and actually do 2 steps in one here. I'm going to distribute the 1/4. At the same time, I'm putting the c back in. Hopefully that doesn't distress us. I'm just going to go ahead and do both of those at the same time. So 1/4 times 2/5 gives us 1/10. And our u was 2x minus 1 to the 5/2 plus the 1/4 times the 2/3 gives me 1/6. 2x minus 1 to the 3/2 plus c. And that's our very first algebraic substitution. Okay, we okay? All right. Pretty awesome, right? I love this. All right, so let's take a look at the next one. So here we would say u equals 1 plus x squared du is going to be 2x dx. Move the 1/2 over. So we've taken care of the 1 plus x squared, and we have taken care of one of the x's. Y'all see that? One of the x's is taken care of right here. But I have 4 x's left to deal with. So let's try our technique with algebraic substitution. I'm going to take my original, and I'm going to solve for x squared. So that'd be u minus 1. And I'm not going to square root. I actually need 4 x's. That gives me 2 of them, right? I need 4. So I'm really going to need to use this twice. You with me? I'm using this twice to take care of 4 of the x's. That takes care of the other one. And then my regular u substitution. So we have 1/2. I would have u to the 1/2 here. That x to the 5th is split between, I need 4 of these. So u minus 1 to the 4th. Oops, squared, because it's x squared. And then one of them is handled by this x. Okay, so u minus 1 squared, that gives me 4 of them. And then one is handled by this, and that's du. Now, again, we don't have product rule or chain rule or anything like that. So we are going to have to FOIL that out and distribute the u to the 1/2. So let's kind of try to get some of this done in our head. So this distributed would be u squared minus 2u plus 1, right? I distribute the u to the 1/2 to those, and I get u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. So I did a couple of steps at once. I FOILed it out and I distributed the u to the 1/2. We good? Now we do our reversal power rule. Okay, so 5/2 plus 1 is 7/2. So 2/7 u to the 7/2. 3/2 plus 1 is 5/2. So 2/5 u to the 5/2. And 1/2 plus 1 is 3/2. So 2/3 u to the 3/2 plus c. I'm going to do the same kind of thing I did before, where I'm going to go ahead and distribute the fraction at the same time that I'm putting the u back in. All right, so we're going to do that. So I'm distributing the fractions, cleaning the constants up, or the coefficients, and then I'm going to put the u back in. So we'll get 1/7, and our u was 1 plus x squared to the 7/2. And then our next fraction will be negative 2/5, 1 plus x squared to the 5/2. And then we have 1/3, 1 plus x squared to the 3/2 plus c. Okay, and so that is our answer. All right, pretty straightforward, right? We're just adding one little wrinkle to it. Most of the stuff we already know how to do. Okay, the very last one is a definite integral, so looks like we're going to have to do algebraic substitution, and I'm going to change the bounds because that's just the way I prefer to do it. So this last one, we'd say u equals 2x minus 1, du equals 2 dx. So 1/2 du equals dx. Then I have an extra x left over, so let's do our algebraic substitution piece. Let's solve this original u sub for x. So we get u plus 1 equals x. 1/2 times u plus 1 equals x. All right, let's go ahead and change the bounds. Don't you want to get all the u stuff done? So u is going to be 2 times 1 minus 1. What is that? 1. And then u is going to be 2 times 5 minus 1, which would be 9. So rewriting our integral, let's see, we have a half here and a half there. So that's 1/4. Our new bounds are 1 to 9. let's see what else we got going on. We got a u plus 1 in place of the x. I already pulled the 1/2 out. And then over u to the 1/2 du. Okay, we okay? At this point, we use the technique that we did the other day, right? We just split this into two different quantities. This part, u over u to the 1/2 and 1 over u to the 1/2. We rewrite it. We get 1/4 integral 1 to 9 of, let's see, u over u to the 1/2 is simply u to the 1/2. And 1 over u to the 1/2 is u to the negative 1/2. So we do our integration, and we get 1/4. See, we add 1, so that's 3/2, so 2/3 u to the 3/2. Plus, let's see, 1/2, negative 1/2 plus 1 is a positive 1/2, which is multiplied by 2 u to the 1/2, evaluated from 1 to 9. Now, just for time's sake, I'm not going to sub that in and work through the arithmetic with that. I will tell you what, if you do that, you will come out to have 16/3 as your answer once you do your f of b minus f of a. And so that's algebraic substitution. How are we with that? Everybody okay? Okay. These last examples down here are, there will be some times where knowing information about even and odd functions is going to be to your advantage, with integration especially. So if a function is even, and we've talked about even functions before, an example of that would be the parent parabola. That's an even function. It's symmetrical about the y-axis. If you're told that you have an even function, or if you can determine that you have an even function, and we're integrating from, say, negative 2 to 2, we're equidistant on each side of the y-axis, then we can change this to 2 times 0 to a of f of x dx. Now, why might we want to do that? It might be easier to integrate from 0 to 2 than negative 2 to 2. 0 is kind of nice to use. It also will be especially helpful when we work with polar integration, which is later, which, if it's symmetric, we can do that kind of thing as well. We can go from 0 to, whatever. So it's just a helpful technique that isn't going to go away. You need to know how to work with an even function. An odd function has symmetry around the origin, and an example of an odd function would be x cubed. And so I think logically, if we think about this logically, if I integrate from, say, negative 2 to 2 of an odd function, what am I going to get? I'm going to get 0, right? And so that's a handy piece of information to know, that if it's an odd function and I'm integrating like that, I am able to get 0. That kind of cuts our work quite a bit down, doesn't it? If we can say, oh, it's 0. All right, so there's a few problems that we're going to work in the abstract. This would be like something you might see as a multiple choice problem on the AP test, or maybe even one of the portions of the free response. So we're told that f of x is even, and we're given one piece of information about it, that from 0 to 5 of f of x is 3. So knowing that it's even, would we be able to figure out what the integral from negative 5 to 5 would be? We would, right? Because this is this formula that we just did. This is the same thing as 2 times 0 to 5 of f of x dx. And so we know that's going to be 2 times 3, or 6. Okay? Would we be able to know this one from negative 5 to 0? Yes. What would that be? It would actually be 3. And what about negative 5 to 5 with a 4 in there? What would we have to do? Yeah, just take that out, right? And multiply by 4. So this is going to be 4 integral negative 5 to 5 of f of x dx, which is 4 times 6, or 24. Okay, pretty straightforward, right? We okay? All right, let's look at some problems having to do with odd. We're told that f of x is odd, and that the integral from 0 to 5 of f of x is 3. So if we look at the integral from negative 5 to 5 of f of x, what would we know that would be? It's going to be 0. What about negative 5 to 0? Oh, good catch. -3, right? -3 because it's on the other side. It's opposite of this. And from -5 to 5, a 4 f of x is simply just going to be 0, right? 4 times 0, which is just 0. Okay, how are we with the even odd? Okay, great, great. No, just the writing that I did is the justification right here and here. Okay. On the next slide, I actually added a couple of things to the next slide. If you have printed it off already, I'm going to point out to you which things that I added. So this portion right here, the writing in these boxes, was on the old slide. I mean, I retyped it so it looks a little different, but it's the exact same stuff. This example and this example are on the old slide. So the new things would be this formula's pretty important. So copy that little guy down. See if I can get that out of the way. Okay. It is. I uploaded the new slide last night, so if you would rather just print the new slide, you can. The only things that I've added are this formula over here and this first problem. Okay? So, it would be kind of fun to go through all the text and explain to you every little thing about all those words up there, but actually there's only a few things that we need to know. These formulas are primary. We need to know the right endpoint formula and the delta x formula. The left endpoint is important. I've never seen them use a left endpoint on the test, and I'm not going to use a left endpoint, but you know, it is different. This is Riemann sums. We are relating Riemann sums to integrals. It's like the definition of an integral is a Riemann sum. And so that's what we're working with. So these two formulas are going to be important, and this, out of all the text in the top, the most important things to remember are these two formulas and this format. Okay? That will get you what you need on these problems. So let's talk about this format just briefly. This is the definition of an integral. It's in Riemann sum. The limit as n goes to infinity, we hopefully recognize that symbol. It's a summation symbol we worked with in pre-cal. K equals 1 to n of f of ck times delta xk. Now, they use k's, they like i's, the variable could change. You know, k or an I are the typical ones. But those are the three most important things. And so what we're going to do is we're going to actually go both ways. I'm going to take an integral and turn it into a Riemann sum, and then we're going to take a Riemann sum and turn it into an integral. These two questions are questions from the AP test. They are fascinated with Riemann sums, just like they are fascinated with definition of the derivative, right? I mean, they love the basic definitions of those things that we do all the time, derivative and integrals. So this is, we're going to be working both ways. So let's go through and let's change an integral into a Riemann sum. So I'm going to write down our little formula, delta x equals b minus a over n. And of course, we're familiar with a and b. A and b are the bounds, a and b right here. N is the number of, say, rectangles that we wanted. If we wanted 5 rectangles, we'd do b minus a divided by 5. That would give us our intervals. So that's a formula from Riemann sums. And so according to our integral, delta x is going to equal b is 1 minus a is negative 2 over n. So delta x is 3 over n. Okay? Delta x is 3 over n. So that's the first piece of information we need. The second piece of information we need is here. So we looked at that. Now we're going to go here. It's C1 or CK. Basically, we can call it CK. The formula is A plus I times delta x. Okay, and actually that would be CI because it's I. So it's this formula right here. Alright, so we know what A is on our bound, right? So CI is going to be A is negative 2 plus I, and we found delta x already. It's 3 over n. So our CI term is negative 2 plus 3I over n. So now we have the basis to build the Riemann sum. That's what we're going to plug into this formula right here. We're plugging into the Riemann sum formula. So we're going to have limit as n goes to infinity of the summation as k equals, starts at 1 and goes to n, of f of this. So hopefully we're familiar with function notation. F of this, that means I take this and I place it inside of the function, right? I take this and I place it inside of the function. What is the function here? 2x. So the 2, I take this guy right here, which is negative 2 plus 3I over n, and I place it inside of the function, which is what I just did. We're here. And then I multiply by delta x, which we said was 3 over n. Now, to pretty it up, do the limit as n goes to infinity, summation 1 to n. I'm going to multiply the 2 times the 3 over n and get 6 over n, negative 2 plus 3I over n. Now, that's as far as I'm going to have you go. Now you know what it's like to calculate a derivative with definition of the derivative, right? You know what that's like. This is twice the fun of that. I'm just saying, it really is. It takes that much work to do it. Okay, so we're not going to complete it. We're not going to actually use the Riemann sum to calculate the integral, although it is quite exciting. All we need to know for the exam is to be able to go back and forth. Can you go from an integral to a Riemann sum and a Riemann sum to an integral? That's it. That's all we're working at. We're not going to actually use the Riemann sum to calculate it because it's pretty intense. So we're just going to stop. And that would be this is the representation of this integral in Riemann sum form. Okay, so now let's go backwards. Yes? It should be, they should match. Should be I and I. Yeah. It should match. Yep. This had K. I was just copying that down, but it has to match the variable that we used. Yeah. Okay? So, now we're going to go backwards. We're going to turn this Riemann sum, and this is actually expanded. This is a Riemann sum expanded. We're going to turn this into an integral. Okay? And I've seen them go both ways on the test. I've seen them give an integral and say which Riemann sum is it in a multiple choice question, and I've seen them give the Riemann sum and say which integral is it. So we're going to go the other way. All right. So that is really talking about this formula right here. That's the expansion. This would be C1, that would be C2, and that would be whatever variable we're in, CK or CI. That's our general term. Okay, so what we're working on is this right here. Okay, so our f of ck or cn, whichever variable we are, is f of a plus I times, well, let's use a k, times delta x. Okay? Okay. So I'm copying my formula down into my function. That's all I'm doing. F of ck is f of, and I'm sticking in that right endpoint, a plus k or I, whichever variable you want to use, delta x. I'm just setting up my formula right now. I'm not done anything yet. Okay, I'm setting up my formula. So here's my formula. I need to match my formula to, so this right here, I'm matching it to what my general term is right here, 5 plus 3n over n. Okay, we're matching it up. So, well, that's part of the function. That's the function. And so what, according to this breakout, what is my A going to be? A is 5. If I didn't have a number here, what would A be? 0. Okay? My A is 5. Plus K or I, whichever one you're doing, times delta X. The K or I is this. So what's my delta X? 3 over n. Okay? And you may have to go back and listen to this part of the video because I know it's real complex. So that's my A, that's my delta X. I have this formula right here that relates the A and the delta X. So 3 over n equals B minus 5 over n. So what's my B? 8. Once I have my A and B, I have the bounds of my integral, right? My bounds are from 5 to 8. And according to this format right here, what is my function? X squared. That's my integral. That's it. Okay? Now, we really don't have time to do this last one, so what I'm going to do is I'm going to circle the answer, and I encourage you to try it on your own and see if you can get that. Question. Where? Why is this right here? They're using a variable n instead of a variable I. Okay, that's the way. So this is, now let's go back here because we're getting confused going backwards. Let's look at this right here. Okay, this is the original one that we did. We put the CK inside of the function. This is my CK. I put it inside of the function, which was 2x, right? We go over here. Look what they did. They put the CK inside of the function. What is the function? It's x squared. Okay? That's the same kind of thing we did over here.
So by looking at that, we can pretty quickly go, oh, it's x squared.
Right. Exactly.
So then the real task is just figuring out
Finding your bounds are. Yes, finding your bounds is this work over here. And again, you may get to where you can do that in your head. You don't have to write all that out. It's going to be a multiple choice question, and well, I haven't seen one that's not a multiple choice question. Question. They did for whatever reason. Because in order to solve the limit, you do have to take the summation out, and that's a procedure that we're not going to do, right? Because, like I said, no. It represents which term you are, the ith term, or whatever variable they're using, the kth term, or the nth term. It's all, they just love to use all those different variables. It's the, depending on what variable we're using here, you know, they use a k right here. They're using everything in terms of k or an I. It just depends on which variable you're using. I switched it over here because the I, we need to match those up. Yes, it was because that was back a little bit ago. We talked about that. It was because this was a k and I was copying the formula, but this was an I. So I fixed it. Yes. Okay? All right.